Hello and welcome. I am Melanie Ross, and I will be the facilitator of this webinar today. Our presenter is Emma Dutton. Thank you for joining ANAB for our complimentary webinar on Just the Facts, Requirements and Statistics. We are giving this webinar to provide further guidance on statistics for laboratories. Please note, we are recording this webinar, so it will be available for viewing in the future. A little bit about our presenter. Dr. Dutton, an instructional designer for ANAB, has provided instruction on a variety of conformity assessment topics to the forensics community since 2013. Prior to joining ANAB, Ms. Dutton spent more than 11 years as a quality assurance manager in a forensics laboratory. Her portfolio includes over 12 years performing research and development in pharmaceuticals and biotechnology industries, as well as teaching biology as an adjunct professor at several universities. Some logistics before we get started. Due to the high attendance, everyone will remain muted for the duration of the webinar. Please enter your questions into the Q&A box. We have planned time at the end of the webinar to answer questions asked. And again, we are recording this webinar. With that, Emma, I'll turn it over to you.
Thank you, Melanie, for that introduction. I just want to say hello and welcome everyone. And let's get started with talking about statistics. Who needs that? Well, we do need to know that between ISO 17025 and 17020, there are multiple requirements that call for selecting and applying statistical techniques and methods for processing and analyzing data, as well as sampling plans, reviewing results, and for interpreting results. So for this afternoon or this morning, some of the key takeaways are for us to review the requirements. Let's look at 17020 and 17025 and those requirements that specify the use of statistical techniques and or methods. I hope that at the end we'll understand the importance of statistics when analyzing and interpreting and reporting on data, as well as learn a few statistical techniques that are applicable to the requirements for the analysis of data and for the review and interpretation of the results. So what is statistics? Statistics is the science of the collection, organization, analysis, interpretation, and presentation of data. It is a tool based on theoretical approximations, best estimates, and arbitrary choices, and it's based on the history of the measurements that we make. It is not absolute, and it doesn't give absolute answers as much as some like to think. Statistics is just a way for us to do some data analysis and data interpretation. There are two fields of statistics. We can use descriptive statistics, and we can use inferential statistics. And there are requirements in 17025 that ask us to use both of these types of statistics. Descriptive statistics organizes and presents the raw and summarized data. It is things like the mean, median, and mode, which we're probably most familiar with, in addition to standard deviation, quartiles, etc. We can also descriptively look at our data in graphs, tables, and charts. Inferential statistics, on the other hand, is used to draw an inference about a population. So we do what is called sampling, and then through the analysis of that sample, we can draw an inference to the whole population. This is a way to quantify, like uncertainty. We must consider the data relative to some hypothesis. Basically, when we do inferential statistics, there are some assumptions, like how likely is it that we would get the data results, like the data results that we have. And we must have some understanding of probability as well. Following is a list of the requirements that mentions or infers the use of statistics. Most of these are in 17025, from selection and verification of methods to sampling to the evaluation of measurement uncertainty, which is the one requirement that infers the use of statistics, also to ensuring the validity of results and reporting statements of conformity. And for inspection methods and procedures, it also brings in having sufficient knowledge of statistical techniques so we can apply it to statistically sound sampling and for processing and interpretation of results. So let's take a look at these requirements. For 17025, 7.2.1.1 says the lab shall use appropriate methods and procedures for all laboratory activities and, where appropriate, for evaluation of the measurement uncertainty, as well as statistical techniques for analysis of data. In addition, in 17020, there's a similar requirement in 7.1.2, where it says, where applicable, the inspection body shall have sufficient knowledge of statistical techniques to ensure statistically sound sampling procedures and the correct processing and interpretation of results. And if you want to think about processing and interpretation of results, it really is analogous to the analysis of data. So let's dig into some of the statistics that is used for analysis of data. So you have to think, when do you analyze data? And that's primarily what we do. We analyze data in the laboratory in multiple different arenas. When we do method validation or verification, there's data to analyze. We have to process the data, interpret the data, and use statistical techniques to analyze that data. For any inspection, test, or calibration result or data that is generated during those activities, we have to review the data, review those results, and in some cases, apply statistical techniques. We also need to evaluate or estimate uncertainty data for measurements that we make, and we have to ensure the validity of the results and use statistical techniques where applicable for the analysis of this data as well. So let's look at some of this data analysis that we do in the laboratory. And we'll start with method validation and verification. For any method adopted or used, whether it be a standard method, non-standard method, or laboratory developed method, we need to determine if the method is fit for purpose. We do that by performing either validation or verification. When you establish the performance characteristic of a method, this is validation. If you are confirming that the method performs according to specified or already established performance characteristics, this is a verification. Either one, validation or verification, they use similar approaches and they use similar statistical analyses when evaluating these performance characteristics. If you want more information on validation or verification, there is current training that is available. You can see the ANAB.org training website for further details. But let's get into some of these performance characteristics. So some of the performance characteristics that are often reviewed or analyzed during method verification or validation are listed here, from accuracy, precision to bias, repeatability, reproducibility, even measurement uncertainty, as well as things like linearity, selectivity, specificity, cross-sensitivity, or robustness. These performance characteristics, when you're analyzing or evaluating these performance characteristics, you use statistical techniques. For example, when looking at accuracy, accuracy is the closeness of agreement between a measured quantity value and a, quote, true or known quantity value. It's influenced by both precision and bias. You're all probably very familiar with the target analogy of bias and precision. You can statistically calculate precision and bias. As you know, precision is the dispersion of the quantity values around the target value. This is what we're trying to achieve. And in the targets example on the left, you can see that there is low variance or good precision in the top two targets, where those quantity values or the small dots are closely spaced. In the bottom part of the graph, of course, there's high variance or low precision. That is, you'll have a larger value associated with this. Well, we can statistically calculate the variance or the precision. And if you look at the graph over on the right hand side, the precision is the spread of those quantity values around that mean. One measure of precision is a measure of dispersion, and that can be the variance or the standard deviation, which is typically what we use when we do repeatability and reproducibility studies. We estimate the mean, the variance, and the standard deviation. And that is giving us an estimate of precision. How dispersed are these quantity values around the mean? In addition, we can also estimate bias. Bias is systematic measurement error. It is a component of measurement error that in replicate measurements remains constant or varies in a particular manner. You can assess bias or that systematic measurement error by comparing the measurement result or the average to a known reference value. So in the example presented here on the right-hand side, we have quantity values, those things that we measured. The average is 500.03, and if we wanted to estimate the measurement error, we would take the quantity value and subtract it by the known reference value to get to the measurement error. To get the systematic measurement error, or the bias, we would take the mean value and subtract the known reference value, which is 500 grams. And in this case, 0.03 is the bias or the systematic measurement error from these measurements. This is, again, a measure of measurement error or bias. It tells us something about the measurements that we're making, and it is a part of the overall measurement error for these measurements that were estimated. So in addition to accuracy, precision, and bias, there are some additional statistics that we use when we're evaluating our performance characteristics for any validation or verification study. Additional performance characteristic could be linearity. So we have to ask ourselves, what do we use linearity for? How could we go about looking at the linear range of our measurements that we're making? One way of doing that is by doing regression. The data is what it is, but if we can find a mathematical model that's appropriate for the data, we can use that model to predict outputs given hypothetical inputs. So in this case, regression models are often those linear trend lines, but they can also be quadratic, exponential, logarithmic, or logistic. For us, we typically perform serial dilutions of a known reference concentration. We perform this linear regression, and this helps us to determine the linear range of our quantitative method, helps us determine the background and where we need to set that background, and it also helps us to set the detection limits. Where do we have our lower detection limit, and what are our limits of quant, both in the lower and the upper quadrant? The statistic behind linear regression is a process of using numerical data pairs to calculate the slope, or the M of the line, and the intercept B of the line, and give that best trend line, or that best fit for that line, using the equation y equals mx plus b. And that helps us model that data. Sampling comes in numerous aspects of the types of tests or inspections or calibrations that we perform. And there are several requirements, both in 17025 and 17020, that asks us to have sampling plans and have these plans based on statistical methods, to have sampling methods for how we select samples. And again, part of our method is our sampling plan, as well as to use statistical techniques for our sampling procedures. So let's look at sampling. To look at sampling, we first have to know, what is a sample versus a population? A population is any group of interest we can describe. It's used in statistics really to represent all possible measurements or the entire collection of measurements that are of interest to us in any particular study. If we do a numerical characterization of that population, it's called a population parameter. A sample, on the other hand, is a subset of that population, and it's used in statistics to represent a subset of the measurements from the population that is representative of that population from which it's selected. We often don't have the luxury of measuring all the components in the population, So we're most often having to select a sample of that population, and that numerical characteristic that is associated with that sample that we select is called a statistic. So it represents the population. So let's look at some sampling strategies, because these sampling strategies are very important when we come to select the samples that we're going to use to represent the population. So some sampling strategies for selecting samples include random sampling. We're probably most familiar with random sampling. This is you randomly go out, select a sample, and any sample within that population has an equal chance of being selected. Sometimes we don't do random sampling. We might do something called stratified random sampling. In this case, we have a population and we divide that into homogeneous subgroups or strata. And then the samples are randomly selected from those subgroups. Some examples of the subgroups could be we could divide the population into male versus female, or education level from high school to BS to master's to PhD. And then within those strata, select samples randomly to test. We could do what is called cluster sampling. This is where the population is divided into smaller heterogeneous groups known as clusters. And then from those clusters, you select a few of those clusters randomly. And within those randomly selected clusters, you sample all within that cluster. An example given here is that you could divide the United States up into zip codes, which we are divided up into zip codes, and then select 10 of those zip codes out of the 200, and then all of the individuals within that zip code you would sample. Systematic sampling is a way to sample where you choose every 10th sample. So you'll have your samples lined up and say, okay, we're going to choose, every 10th sample. And it's somewhat random, but in this case, you're doing it in a systematic fashion. Convenient sampling is probably the least likely that we would use, although in some cases we might use convenient sampling in the laboratory. But in this case, it's just an easily available sample that you get wherever you can. For instance, one of the best ways or the best examples of a convenient sampling is that you go to a football game and you're standing there, and as people are coming out of the football game, you select a person and you ask them, what did they think? And so it's not really random, but you're conveniently selecting the people that happen to be coming out. So of course the people that like that team are going to be going to the game to see the game, and would most likely be representative or have some bias towards that team. So just to give you some examples of those sampling strategies and how they might be applied, simple random sampling, you just randomly select out of the population. It could be that for laboratories that do seize drug analysis, maybe you get in a bag of pharmaceutical pills. It's not a homogeneous population, or it's a homogeneous population, so you just randomly select out of that 1,000 pills in that bag that all look the same, a number of samples. Systematic sampling, again, is taking systematically, like here they're showing 1 out of 2. So you pick 1, skip 2, pick 1, skip 2, pick 1, skip 2. Stratified sampling, break them up into strata. Here we have male, females, and then you randomly select out of that stratified sample. And then, of course, cluster sampling, you just divide them up into groups, and they could be heterogeneous groups, and you randomly, you sample all of the population within that group. So some different types of sampling that we do within the laboratory. Think about how you're doing your sampling. With each type of sample that you select, you also need to consider some of the biases that go into selecting of that sample. When we do sampling, there is not only how we select the samples, but also how we make that inference. And in this case, this is the inference part rather than the descriptive part of statistics. So during a sampling plan, it says wherever possible, use a statistically based sampling plan. One of those statistically based sampling plans is called the hypergeometric distribution. In this case, hypergeometric distribution is a discrete probability distribution that describes the probability of successes in draws without replacement. So this is a table from the UNODC guidelines on representative drug sampling. And what it is saying, for instance, if you get a population of 100 items in, from those 100 items, if you were to select 23 of them and test them, and all 23 came back with the same result, then you can say with a 95% confidence that 90% of that 100 population is the same. I'm not going to go into this statistical calculation up here where it gives you the p-value. And the p is the probability of obtaining exactly x successes, where k is the number of successes in the population, x is the number of successes in the sample, n is the size of the population, big N is the size of the population, with little n is the size of the sampled, and the kcx is the number of combinations they're taken. So I'm not going to go into how this statistic was derived, but if you have additional questions about using the sampling plan or additional sampling plans, there is additional information out there, especially for those that are doing the seized drug analysis from this guideline. So the next requirement talks about 7.6, evaluation of measurement uncertainty. In this requirement 761, it says when evaluating measurement uncertainty, all contributions that are of significance, including those arising from sampling, shall be taken into account using appropriate methods of analysis. So there are two types of methods of analysis, and this is the one requirement that kind of infers the use of statistical techniques for doing this, because the two methods of analysis are type A and type B. Type A method of analysis is a method of evaluating the uncertainty by statistical analysis of a series of observations, and that is what is inferred in this requirement. Type B is a method of evaluation of uncertainty by means other than the statistical analysis of a series of observations. But for some types of type B analysis, you still could employ statistical techniques. So let's look at type A and type B methods of analysis. Type A method of analysis, and this kind of goes behind some of the performance characteristics that we were talking about earlier as well. This involves the evaluation of a series of measurements, and those series of measurements could be obtained through repeatability or reproducibility studies. The data is analyzed statistically by calculating the mean, variance, and standard deviation, as previously shown in a previous slide. The variance and the standard deviation, as previously mentioned, give you that information about the precision in the measurement, and it talks about the dispersion of those quantity values. So when you're estimating an uncertainty of measurement, it's really the standard deviation that gets expressed, and the standard deviation that is expressed is taken to be the standard uncertainty that gets plugged into the root sum square equation. So this is the S, or the standard deviation, that goes into the root sum square equation, which is shown here in the upper right-hand side of the slide as the combined uncertainty, which equals the positive square root of the sum of the weighted variances and covariances. So this is the statistic that's behind estimating the combined standard uncertainty for measurement results, represented as a measure of dispersion or precision as the standard deviation. For type B analysis, this is where we get that information from some other source, but in some cases, we can estimate the uncertainty of measurement using a probability density function. So certainly some other sources of type B data comes from our reference material, certificates of analysis, or from our calibration certificates. But there are some times or some places where we need to take an uncertainty component and estimate the contribution of the uncertainty from that component using these probability density functions. For these probability density functions, it follows the statistical rules that apply for the different distributions. And I'm not going to go into a description or the details about each of these distributions here. If you want additional information on these distributions or on the estimation of uncertainty of measurement, please see the Measurement Uncertainty Practical Applications course posted on the ANAB training website. There are additional requirements in 17025 in 7.7 that talks about ensuring the validity of results. And for ensuring the validity of results, it says the lab shall have a procedure for monitoring the validity of results, and the resulting data shall be recorded in such a way that trends are detectable, and where practicable, statistical techniques shall be applied to review the results. We're pretty good about monitoring the validity of the results. We have a lot of things that we put in place to monitor the validity. We record the data. Sometimes we look at the trends. I'm not sure how often we in the laboratory actually apply these statistical techniques to review the results, but it's not very difficult to do. But in doing so, you really need to know the type of data or the results that you're capturing during these monitoring activities. And think about what type of data do you have? Is it numerical or is it categorical? Because determining the type of data that you have, that you're accumulating, will help you decide the statistical techniques that you want to use for the evaluation of that data. So numerical data is quantitative measurements that have a magnitude on a numerical scale, and you can do math with these and apply some of the mathematical techniques that we've already talked about. Categorical data is qualitative characteristics that do not have a magnitude or a numerical scale. There's no math possible. However, you can still do statistics on categorical data. And there's a whole section in most statistics books that help you look at some of this information or look at categorical data in a statistical way. 4771, here's the list of examples or the list of things that it says to use to monitor the validity of the results. For us in the laboratory, we use a lot of these different ways to monitor that our results are valid, from the use of reference materials or quality control materials, maybe as positive controls, for looking at alternative instrumentation, doing functional checks of equipment, and that would be like the instrument diagnostic checks, using check standards or working standards with control charts. Could be one and the same with doing those intermediate checks, looking at the calibration status of measuring equipment. Some laboratories do replicate testing and then do a comparison of those replicate tests to make sure that they're within a certain percent of one another. You might do retesting, maybe a correlation of results for the different characteristics of items, review of the reported results, intra-laboratory comparisons, and then testing of blind samples. For all of these, you can take the data that is generated from these approaches to monitoring the validity of the results and graphically display them or do statistical analysis by calculating means and standard deviations and variances or even looking to see if there's differences between means and doing some t-testing or f-testing to see if there's differences in the data that's being accumulated. To show you some examples of how to evaluate and look at the trends of the data from the monitoring of the validity of the results, there are a few graphics on the right-hand side. Up at the top graphic, it's showing trend analysis over a period of time with upper and lower control limits. It has warning limits as well, so you can trend out the data. For instance, maybe you're monitoring the calibration status of the equipment, or you're monitoring your uncertainty of measurement to see, how your measurement results are comparing to the variability that's already been estimated on those components. And so you can plot that data out over a period of time in a control chart and do some trend analysis that way. Maybe you're looking at review of reported results, and for the results that have been reported, you want to know on average how many reports went out a month, and out of those reports on average that went out in the month, how many stated a certain type of conclusion. Was the conclusion an exclusion? Was it an inconclusive? Or did they make an identification? And so you can use a frequency plot or chart or a histogram to show that information. What were the reported results that went out the door in that month? Or you can do a correlation of data. You can look, for instance, at the bottom graph, maybe you're correlating positive color test results to a confirmation of an analyte. And you can see that, yes, when there was a positive color test result, the analyte was confirmed. So there's an upward positive slope and correlation of that data. So a lot of different ways to use statistical techniques to evaluate the data, to look at the data. And again, you can do it for both numerical and categorical data. It doesn't matter. You can use these types of graphical displays to look at those trends. One of the last requirements that we're going to discuss is reporting statements of conformity. 7861 talks about statements of conformity, and it says, when a statement of conformity to a specification or standard is provided, the laboratory shall document the decision rule employed, taking into account the level of risk, whether it be false accept, false reject, and the statistical assumptions, and associated with the decision rule employed, and apply the decision rule. So we have to think about what are these statistical assumptions that we're making when we employ decision rules and when we make a statement of conformity. So what are the statistical assumptions? Some of the statistical assumptions that go into the decision rule include that coverage probability that you've used to express your expanded measurement uncertainty. You also have to think about any significance level that you might employ to determine if it meets or doesn't meet a specification, if it's within or not within tolerance, or if it's above or below a stated level of specification. So think about these statistical assumptions that we use. And I guess we first have to know what is a decision rule. So let me give you the definition of a decision rule. A decision rule is a rule that describes how measurement uncertainty is accounted for when stating conformity with a specified requirement. So conformity statements or statements of conformity are specific to those measurements that you're making where you have a measurement uncertainty, and you're basically describing or letting your customer know how you're applying that decision rule to the measurement result to make a statement to say whether or not the measurement result is within or not within tolerance, that it meets a stated specification or it doesn't meet the stated specification, or whether it passes or it fails. And so really, statements of conformity are specific to those measurement results where you have that measurement uncertainty and you're describing how that is applied to that quantity value. So really the statistical assumptions are based on that measurement uncertainty, based on that coverage probability that you selected for that expanded uncertainty, any significance level that you apply, and then the plausibility interval that is used and its complement, that rejection region. When do you accept it? When do you reject it? And there are a couple of ways of doing this and making that statement of conformity. You can do it by a simple acceptance rule, or you can do it with guard banding. Either way this is done, to me, this is analogous to hypothesis testing. You're making an inference, and you're doing it very similar to what would be considered hypothesis testing. So this is just an example of a simple decision rule or simple acceptance rule where you have a stated measurement result with the expanded measurement uncertainty, and you can have the acceptance limits that are stated as tolerance limits. So in this case, the acceptance limit equals the tolerance limit. And again, this is very similar to hypothesis testing, where you would state the hypothesis of that your measurement result equals the specification, and then you would have the probability of a false acceptance or the probability of a false reject depending on the uncertainty of measurement and the tolerance limits that are set. So for example, for many measurements that are made in forensics, it is pretty black and white. We do simple acceptance where we have a known legal specification. For example, illegal weapons are 16 inches or less. And if we do the measurement plus or minus the measurement uncertainty, anywhere that measurement result plus or minus the uncertainty crosses the specification or the legal limit, we cannot say whether or not that measurement result is any different than the legal limit. If it's clearly above the legal limit, we can say it's above the legal limit. If it's below the legal limit where the uncertainty of measurement or error bars don't cross the specification, then we can say it is below the legal limit. Another example of simple acceptance is in the upper right-hand corner where they have upper and lower specifications, and they set their decision rules based on the measurement uncertainty, which is based on the expanded uncertainty that they select or the coverage probability. And they can show that they get a pass, that is, it passes or it meets specification as long as the quantity value is within the lower or upper specification limits. So with that, that is all that I have for you for today, just to show you a bit about where statistics comes into play with the requirements in 17025 and 17020. I gave you a bit about the types of statistical techniques or methods that we use and employ when we're evaluating the data and the results, and how we can use this information to descriptively basically describe the results or make inferences about the data that we collect. If you want additional information, I should say additional information about uncertainty of measurement or statistics and these requirements, we do have a basic statistics course that is new, that is online, and you can find information about this basic statistics as it applies to testing, calibration, and inspection laboratories on the ANAB website at the training website. So with that, I want to turn it back over to Melanie and let Melanie tell you a little bit more about the additional resources and some things that we have coming up.
Thank you, Emma. That was a great presentation. One thing I didn't mention in the beginning is that Emma is one of our instructors for the basic statistics and measurement uncertainty courses that we offer, and that certainly showed in her presentation today. I do also want to note that the basic statistics course is a live online course with a live instructor. We've had quite a few questions come through, and we will get to those after we discuss some additional resources available for accredited laboratories or laboratories seeking an accreditation. ANAB has many different media to further your understanding of standards, accreditation, management systems, and assessments. On the ANAB website, we have free webcasts on a variety of topics. These webcasts are 5 to 20 minutes long depending on the topic and can be viewed at any time. ANAB also has a blog page with a wealth of information related to risk, accreditation, standards requirements, and more. We also host these monthly webinars. And finally, we offer training, as Emma has mentioned, in many different areas, including internal auditing, standard requirements, risk, and a variety of other topics. As with assessments and audits, training has changed significantly with the pandemic and travel restrictions. All of our traditional in-person courses have been converted to live online sessions that include exercises and discussions related to the topic at hand. In fact, we just added a second session of our internal auditor training in February because the first session sold out. So if you see a course that's full, just email us and we'll look into offering more. And finally, we also offer company discounts when multiple people sign up for the same training from the same company. Contact us to find out more. All of these resources can be found on the ANAB website. Now let's get to the fun part, your questions. So Emma, we have a few questions here. If I cannot be technically challenged, I will pull them up. Can't get it to pull up. Okay. The first question is, can you provide an example of a statement of conformity as it relates to ISO?
So I can provide a statement of conformity as it relates to a forensic example. So I'm not quite sure what you mean as it relates to ISO. Since my background is forensics, I'm more familiar with the statements of conformity that are provided in forensic laboratories. And it was similar to the example that I provided here in, and I don't know, Melanie, if you can see me changing the slides now, or you probably have control, so probably don't see the decision rule slide.
Here, we'll give you back control so you can.
That's okay. Yeah. But for me in forensics, an example of a statement of conformity would be letting our customer know whether or not a weapon or a gun is legal or not legal. And so there are legal specifications for the length of a barrel, and it's at 16 inches. 16 inches and below, it's illegal for certain types of rifles. So in this case, they would ask us, is this weapon legal or not legal, based on the legal specification in the statute. And we would tell them that. Based on the decision rule that we use at a 95.45% coverage probability, this weapon measured 15.5 inches. With our uncertainty of measurement, this weapon is not legal. So that's how we would provide a statement of conformity. There may be other examples of statements of conformity that could come, where you have a stated specification. Does this product meet this stated specification? And it would be accept or reject, or yes it does, or no it doesn't, or a pass or a fail, or it's not within tolerance, or it is within tolerance.
Right, yes. One of the examples that I like to give is in water testing, where there's certain microbial limits, and you quantify that, and then there's a limit, and is it above or below? And you have to take that measurement uncertainty into account and have some sort of decision rule for that. So as a non-forensic example, thank you.
Yes,
okay,
exactly.
Our next question is, do labs have to report their particular lab uncertainties, parentheses, site precision, when reporting results from standardized methods that have reproducibility or repeatability that could be larger than their site precision?
I would say go back. Yeah.
Sorry. Go ahead.
Yeah. Go ahead, Melanie. You were going to say it's in reference to?
It's in reference to using published analytical methods such as ASTM.
Yeah. I would say you're going to need to fall back to the requirement and what you require in your laboratory. But there are requirements for reporting uncertainty of measurement. And those I didn't go over for the reporting requirements of uncertainty of measurement. But certainly, let me pull that up. Yes, I have my copy of 17025 right here. So for reporting uncertainty of measurement, there are requirements in 7.8.3.1, which are the specific requirements for test reports. And I would say go there because it does say for reporting measurement uncertainty, you have to report it when or where applicable, when it's relevant to the validity or the application of the test result, when your customer requires it, or when it impacts specification, impacts conformity to specification limit. So I think your example, though, is you were comparing stated uncertainties to your laboratory's estimated uncertainty and when to apply that.
Yes, that's what it looks like from the question.
Yeah. So you would have to evaluate that, the stated uncertainty against what you evaluated in your laboratory, because the uncertainty in your laboratory is going to be more specific to your laboratory and your measurement process, even though there may be stated uncertainties from books or like ASTM methods that say, the use of this method in this process, the uncertainty is X. You may have an uncertainty that is larger from your laboratory. And most often you'll have to go with the uncertainty that's associated with you performing that measurement process within your laboratory.
Okay, great. Thank you. We also had a question early on in the presentation that said, what is meant by decision rule? If you just want to go over an overview of, since we've talked a little bit more in depth, just again, go over what a decision rule is.
So decision rule applies to the uncertainty of measurement and comes into play when you're expressing a statement of conformity. But it's really the rule that describes how that measurement uncertainty is accounted for in that statement of conformity. So again, it's based on the coverage probability that you use and that stated coverage probability. And the example that's given here in this slide, it's really the error bars that are shown in both of these graphics. That is the uncertainty of measurement, and the decision rule is based on that uncertainty and how you set your specification limits, whether or not it is within specification or not within specification. So basically, it's a way to describe the uncertainty of measurement and how that impacts that quantity value, and whether or not you're stating it is acceptable or not acceptable.
Okay, the next question is, what do UR and UO represent in the combined uncertainty equation?
Let me go back to this one. So in this combined standard uncertainty equation, upper right-hand corner, where it's looking at the square root of the summed covariances or variances, the UR, so the uncertainty, which is the standard uncertainty, and R is for like a reference material or a reference standard. And the UO is some other component that contributes to the uncertainty. It could be a standard uncertainty that you estimated using a probability density function when you're looking at readability at tear and readability at load. It could be, so it's just another component that contributes to the uncertainty. And the same for U1, U2, on out. A lot of different things to consider. You could have your uncertainty for the calibration of the measuring piece of equipment, which could be represented here as a UO. Just another component that contributes to the variability of the measurement process.
The next question is, must both type A and type B be used to calculate measurement uncertainty?
I'm not going to say must, but most often, yes, you use both type A and type B. Definitely use type A because that's the uncertainty that's going to come from your measurement process. That is what you estimate by doing those repeat studies. Type B usually comes from the calibration certificates, where you get the uncertainty associated with a calibration. It could come from your reference standards and the calibration of your reference standards and the uncertainty associated with that. It could come from your reference materials. If you're using certified reference materials, that's a type B, where you would get the uncertainty associated with that reference material. So yes, typically, most often, both types are used.
The next question is, how do you decide to move from a linear regression model to a higher order polynomial?
That question is above my basic statistics knowledge to be able to provide you with information regarding when to make that choice. So I would have to defer that to a statistician. For me, I'm not a statistician. I use statistics. Yeah.
Next question. How might the frequency of reported conclusions be used in trend monitoring? If changes in the percentages were noted from year to year, what would it mean? What can be determined beyond reflecting fluctuations in the evidence received? Is there logic?
Yeah. All good questions, and that was just an example that I gave. And it would have to depend on the agency or the company and what you want to look at and what trends you would want to look at. So certainly some of this information could be used operationally for managers or supervisors to decide, what they need, or if they're meeting customers' needs, or if there's consistency in the way that they're reporting their conclusions, and if they need to revisit their reported conclusions and how they're putting that information out. So it all depends. It all depends on what you want to look at regarding the trends in this data. That was just one example that was provided on how you might use statistics to evaluate the data from reports.
Okay. So the next question is, does taking an aliquot of a blood specimen for toxicology testing require a sampling plan? If so, how?
I'm not going to say that it requires a sampling plan, because you have to think about what is your population. You typically get 2 tubes of blood in. You take a sample from 1 tube. You're reporting on what you tested. So it doesn't require you to have a sampling plan and to use statistical-based sampling. In this case, you're reporting on what you tested and not making an inference back to the whole population of that blood. Your sampling,
yeah. Oh, I'm sorry.
I want to follow up on that. Your sampling strategy is probably already stated in your method that you use. That is, you will sample 1 ml aliquot from that blood tube, and that would be your sampling strategy. And in this case, you can go back and say, am I using random sampling, stratified, cluster? So really, you're employing a sampling strategy. You're not using a sampling plan.
Okay, a couple more questions have come in so far. So this one is, under what conditions could sampling with a Bayesian approach be carried out for the analysis of seized drugs?
Yeah, very good question. I'm having to read that again. Is that in the Q&A pod? Could you repeat that?
Under what conditions could sampling with a Bayesian approach be carried out for the analysis of seized drugs?
Yeah, good question. And I'm not a seized drug analyst. I'm only familiar with the sampling that has been done when you have in like a little 1,000 balloons that come in and you don't want to test all 1,000. So you invoke the hypergeometric distribution. Now, of course, if you use hypergeometric distribution and one of the 23 that you tested comes back with a different result, then you have to use a different probability distribution for your sampling, statistical sampling plan. So honestly, I cannot give you a good example of when a Bayesian approach would be used. There possibly are different approaches to the sampling plans that you could use in seized drugs. if you didn't want to invoke the hypergeometric distribution.
This next one I think is more of a statement than a question, but I'll read it off. Verifying decision rule is not equated to a decision point or cutoff in a qualitative procedure.
No, decision rules apply to quantitative measurement results that have an uncertainty of measurement.
And then the final question that we have right now, if you have any other questions, please enter them into the Q&A panel. Can you explain this note in clause 7.6.3 of ISO IEC 17025? In those cases where a well-recognized test method specifies limits to the values of the major sources of measurement uncertainty and specifies the form of presentation of the calculated results, the laboratory is considered to have satisfied 7.6.3 by following the test method and reporting instructions.
Yeah. And this could go back to what the previous individual was referring to about a published test method with a stated uncertainty through it like an ASTM method, where there's been sufficient testing performed to establish the limits of that test method, and then you can apply that. So in some cases, and I think forensics, if this is a forensic lab, in forensics, they're coming to find out that some of the stated and established testing limits that have been put on for angle of impact or area of origin type things where they use that plus or minus 20% is based on some of this, where they've done these studies and repeatedly have shown that the error or the measurement uncertainty always falls within these limits. So I think that's what it's referring to. If there are cases where that test method specifies those values, and it's usually specified because there's been a tremendous amount of validation, verification, repeated testing, and measurements made, that they've demonstrated here are the limits to that test method, and it's always going to fall within these limits.
Okay, well, that's all the questions that we have in our Q&A section. If you give me 1 second, I'm going to take control from Emma again and just go back to our final slides here. We do want to thank you for attending this webinar today. I wanted to put up this contact information in case you have additional questions related to our training or accreditation programs, or you're looking for accreditation services. You can reach Emma at the training at anab.org if you do think of questions after this webinar is over. Thank you again for attending, and the recording of this webinar will be available on the ANAB website shortly.
Thank you, Melanie.
Thank you, Emma.